So again, this is differential equations, and we are going to talk about specifically initial conditions and particular solutions. So if you are looking at the first example here, solve the differential equation f prime of x equals 6x squared and f of 0 is equal to -1. This is a differential equation because it involves derivatives and values of x and y. So this is a differential equation, and then this is what I would call an initial condition. All right, so let's solve the differential equation. So instead of having f prime of x equals 6x squared, I'm going to write it in dy dx form. So that's dy dx is 6x squared, and then dy would be 6x squared dx. And then I can see that this is a separable differential equation because they're are all of the y's on one side and all of the x's on the other side. So then I take the antiderivative here. So the integral of dy is y, and the integral of 6x squared dx is 6 times 1/3 x to the third, and then plus c. All right, so then I can simplify this. So 6 times a third is 2, so y is 2x to the third plus c. Now this is what I call a general solution. All right, so this is a general solution, but then I can use the initial condition to figure out what c is. So f of 0 equals -1 means that x is equal to 0 and y is equal to -1, so I can figure out what c is. So if I have y is equal to 2x to the third plus c, then if y is -1, I have -1 equals 2 times, if x is 0, 0 to the third plus c, and so then I see that c is equal to -1. So then if I substitute that back in here, all right, I have y is equal to 2x to the third minus 1, and that is what I call a particular solution. So this is actually just the same thing that we did before, but now we are taking it one step further to just solve for the c value given some condition that we were told. All right, here is a little bit of a different problem here because we were told the second derivative. So there is the differential equation, and then we were given some initial conditions here, that the first derivative at 0 is 8, and the second derivative, the second derivative was x squared, the first derivative at 0 is 8, and the function at 0 was 4. All right, so then these are the initial conditions. So then what we're going to do is we're going to rewrite this second derivative as d squared y dx squared equals x squared, and then since this is actually just the derivative of the first derivative, then all I'm really trying to do then is trying to tell you that the first derivative will be the integral of the second derivative dx. All right, so that's all I'm trying to tell you here. All right, so now then if I do that, integral of the x squared dx, so that will be 1/3 x to the third plus c. So that was the uh, uh, that's x. That will be the first derivative, but then I need to use the initial condition. So I'll use the initial condition to figure out what this c is. So I know that the f prime of 0 was equal to 8. So f prime of 0 is 1/3 times 0 cubed plus c, that was equal to 8. So then 1/3 times 0 cubed is 0. So 0 plus c is 8. So c is 8. So the first derivative is 1/3 x cubed plus 8. Then I know that the f of x similarly is the integral of f prime of x dx. So that will be the integral of 1/3 x to the third plus 8 dx. And so then if I find this integral, it's actually 1/3 times 1/4 x to the fourth plus 8x plus c. Or if I combine or simplify here, I have 1/12 x to the fourth plus 8x plus c. So that is f of x. But then I can use the initial condition f of 0 is equal to 4 to figure out what the c is for f of x. So let me move that up a little bit here. So now I have f of 0 is 1/12 times 0 to the fourth plus 8 times 0 plus c is equal to 4. And hopefully, I don't know why the paper keeps on sliding down, but half of these pins are garbage actually. I'm going to get rid of that one real quickly. Alright, so now we have, of course, 0 plus 0 plus c is equal to 4, so c is 4. So then f of x is going to be 1/12 x to the fourth plus 8x plus 4, and that is what I call my particular solution. Alright, so this one was a little bit more difficult because you had to find the first derivative and then go back and also backtrack and find the function after that. So again, if you have any questions, please ask, but I feel like these are not too difficult to do as long as you make sure that you are finding the derivatives and the integrals correctly. So because I want to make sure that we get to everything, I'm going to let you do the you try problems later, because they're not that difficult actually, but I do want to look at the page 255 so that we can try to do a few of these more difficult ones. Alright, so now we have a differential equation right here, and then we have an initial condition. So here's a differential equation, here is an initial condition, and then all I need to do is make sure to separate the x's and y's and then integrate and then substitute in the initial condition to figure out what the c is, and then I'm done. All right, so I'll rewrite this as, well, I'll write it as square root of x plus square root of y dy dx is equal to 0. I'll subtract the square root of x, so square root of y dy dx is equal to negative square root of x. Then I'll write it in differential form, so square root of y dy is negative square root of x dx. And then I am ready to take the integral on each side because I have the x's and the y's separated. So integral, integral. So I may wish to write this as a y to the 1/2 and x to the 1/2, so that it's easier for me to visualize using the power rule for integrals. So if I use the power rule, I have y to the 1/2 plus 1 over 1/2 plus 1, and that's equal to negative x to the 1/2 plus 1 over 1/2 plus 1 plus c. So then if I go ahead and I simplify here, I have y to the 3 halves over 3 halves equals negative x to the 3 halves over 3 halves plus c. And then I can multiply by the reciprocal instead of dividing by 3 halves to get 2/3. Y to 3 halves equals negative 2/3. And then x to the 3 halves plus c. And then I can go ahead and substitute in the initial condition. So then if I do that, then I I will have, all right, so here x is 1 and y is 4. That's what that y of 1 notation means. So x is 1 and y is 4. So 2/3 times 4 to the 3 halves minus 2/3 times 1 to 3 halves plus c. So then 2/3 and then 4 to the 3 halves is actually the 2 in the denominator means square root. So it's a square root of 4 to the 3rd power. And then, oh, did I put equal? I did not write equal. Okay, equals negative 2/3, and then 1 to the 2/3 power is 1 plus c. And then square root of 4 is 2, so you have 2/3 times 2 to the 3rd, and that's negative 2/3 plus c. And then 2 to the 3rd is 8, so you have 2/3 times 8 equals negative 2/3 plus c. And then you multiply here, so 8 times 2 is 16, so you have 16 over 3 equals negative 2/3 plus c. So then you add that here, so you have 18/3 equals c. So then the equation becomes, all right, it becomes 2/3 y to the 3 halves equals negative 2/3 x to the 3 halves, and then c was 18/3, so plus 18/3, and that is what I call a particular solution. Now, I wasn't going to say this, but I feel like, Howard, you might actually enjoy this. So if I look at the 2/3 y to the 3 halves equals negative 2/3 x to the 3 halves plus c. And then I look at all these fractions and I really don't want to deal with them, right? I could just divide these all by 2/3, and then what I see here is that I have y to the 3 halves equals negative x to the 3 halves, and then that plus, all right, that's plus, and then I could make this into, right, it could be 3 halves c. All right, so then if I do that, then what I would do is I would still substitute in the 4, and then still substitute in the 1, and then I can just go ahead and make this end up being 8, and that was 1, and this is 3 halves c, and then I add the 1, so that's 9, it's 3 halves c, and then I multiply, and I still get 18/3 as c. All right, so this actually, I think a trick like this actually makes it so that I don't have to worry about dealing with all of those fractions. All right, so just keep that in mind, that things like that are also legal moves, just to simplify everything that you're looking at. All right, so now that I messed up that piece of paper, let me find another one for this next example here. Another, I see. All right, so now let's go to the next one here. So we have problem F. du dv is uv sine of v squared, and then u of 0 is equal to 1. So now what I think that I need you to remember is just to keep the variables straight, all right? Because in all the other ones we've had dy, dx. So you have to make sure that you know which variable is which. So this is the differential equation. And then this is the initial condition. And I see here that I can go ahead and try to get all of the U's on one side and all of the V's on the other side. All right, so I can do that by just dividing by U and multiplying by dV. So I have 1 over U du is V times sine of V squared dV. So now I've separated the equation so that the U's are on one side and that the V's are on the other. And then I can go ahead and take the integral on each side. So integral. So the integral of 1 over u du, that's one that we talked about before. That's the natural log of the absolute value of u. And then for this one, I would say use a substitution, but because we already have a u in the problem, we might want to use like w. So w is v squared, and then dw is 2v dv. So we have 1/2, and dw will be v dv. So here's the v dv. So v dv is equal to 1/2 dw. So 1/2 dw. And then since v squared was w, we have sine of w. And then I'll bring the 1/2 out in front. So I have natural log of the absolute value of natural log, there we go, of the absolute value of u is 1/2 integral of sine of w dw. And then if I find the antiderivative of sine of w, that will be, all right, so that will be, well, that's negative cosine of w plus c. And then I can go ahead and substitute the w back in. So that was v squared. So natural log of the absolute value of u is negative 1/2 cosine of v squared plus c. So then I see that this is my general solution. All right, so this is a general solution to the differential equation, but then I know u of 0 is equal to 1. So make sure that you know which letter is which. So the letter that's on the inside is v, so v is 0, and then u is equal to 1. So then I substitute the 1 for u and the 0 for v. So natural log of the absolute value of 1 is equal to negative 1/2 cosine of 0 squared plus c. So natural log of 1 is 0, and cosine of 0 is 1. So then if I add the 1/2, I have 1/2 is equal to c. So that is the constant of c, and then I can substitute that in to figure out the the particular solution. So there we go. So we substitute the c into the general solution to find the particular solution. So natural log of the absolute value of u is negative 1/2 cosine of v squared plus 1/2. And this is what I call the particular solution. All right, so I hope that you enjoyed this. So let me figure out where the next page is. So again, if you have any questions, here we go. A ball is thrown vertically upward from a height of 5 feet with an initial velocity of 64 feet per second. So the acceleration due to gravity is negative 32 feet per second. Find the position function given the height s is a function of the time t, and how high will the ball go. So the first sentence just tells us the initial condition. So the initial conditions are that, all right, the initial conditions are that the the height is 5 feet and the velocity is 64 feet per second. And so then they tell us the acceleration. So the height function is always s. All right, they told us to call it s, and they told us to call t time. So this means that essentially initial means at time t equals 0. All right, so this will be s of 0 is 5 feet. S prime of 0 is 64 feet per second. But now we know that the a function that we want to find is going to be s of t. So that's what we want to find, but they tell us s double prime of t, the acceleration. All right, acceleration is actually, yeah, okay, you're right. I spelled acceleration wrong. Okay, so yeah, so the acceleration then is the negative 32 feet per second squared. So acceleration is negative 32 feet per second squared. So then I can use that information to figure out what the velocity is and then what the height is. So s prime of t will be the integral of s double prime of t dt. And then remember that s of t will be the integral of s prime of t dt. All right, so this is like one of the examples that we already did, but we had to write out the initial conditions and everything ourselves from the information that was given here. So s prime of t is the integral of negative 32 dt. So that will be negative 32t plus c. Now, if that's s prime of t, we can use the initial condition s prime of 0 is equal to 64 to figure out what the c is. So we have s prime of 0 is negative 32 times 0 plus c is 64. So 0 plus c is 64 and c is 64. So that means that the velocity is equal to s prime of t, so that's negative 32t plus 64. When I substitute the 64 in right here, and then I can find the height function or the position function by finding the integral of s prime of t dt. So s prime of t was negative 32t plus 64, and so then s of t will be negative 32 t squared over 2 plus 64t plus c. All right, so that's the, oh, yes, how did we assume that the acceleration was negative 32 feet? Well, that's what the problem said right here. So then if I simplify this, then I get the height is, so remember this is the height or the position. So that will be negative 16t squared plus 64t plus c. And yes, so acceleration will always be the second derivative, right? And so then the s of 0, the initial condition for the height right here is that it was 5 feet. So s of 0 is negative 16 times 0 squared plus 64 times 0 plus c is equal to 5. So that means that c is equal to 5. So then if I substitute in the 5 right here, I get s of t is negative 16t squared plus 64t plus 5. So this is the particular solution, and then so before I go on, like just like hopefully there aren't too many pieces of confusion here, but I do want to make clear that the acceleration is always the second derivative, the velocity is always the first derivative, and the position or the height is always the the s function, the original function. But then the second part though asked how high will the ball go? So how high will the ball go? That means to find the maximum height of the ball, and to do that I need to actually just set the first derivative equal to 0. All right, so that's where I find the possible maximums are where the first derivative is equal to 0. So remember that the possible maximums occur when the first derivative, s prime of t, is equal to 0. So then s prime of t was negative 32t plus 64. So I set that equal to 0. Then I subtract the 64, so negative 32t is negative 64. Then I divide by negative 32, so t is equal to 2. So the the ball will reach its maximum height after 2 seconds. So the ball will reach its maximum height after 2 seconds. But that doesn't tell me how high the ball goes. To figure out how high the ball goes, I need to find the s of t. So s of 2. So then the maximum is actually, the maximum height is actually s of 2. So that's negative 16 times 2 squared plus 64 times 2 plus 5. So then if I go ahead and I calculate that, all right, so I I feel like if I don't double check with a calculator, I will make some sort of mistake. But yeah, so 69 feet. All right, so this is 69 feet will be the maximum height that this ball will go under these conditions that were given. So if the ball started at a different initial height, like 10 feet off the ground instead of 5, or if the ball started at being launched at a velocity of like 128 feet per second instead of 64, that might make a difference. Well, that would make a difference as well. So those are just things to consider. But yeah, so the ball here is going to always just drop back to the ground or have an acceleration of negative 32 feet per second squared. So again, if you have any questions about this, please feel free to ask. But unfortunately, this is the end of this section here on differential equations.